Stop, the universe is missing 2,000 galaxies. The radio dish was pointed straight at Boötes, but the headphones were strangely quiet. It wasn't a total silence, but the sound felt thinner and emptier, almost like someone had turned the volume down on the entire sky. On the monitor, the source counts kept ticking lower than any of the control fields. Where the team expected to see 2,000 galaxies, only a few lonely dots blinked back from the darkness. The technician muttered something about checking the gain, but even after they confirmed the equipment held steady, the gap remained. The astronomers stared at a 330 million light-year hole in the universe and admitted that it just couldn't be right. Here's the thing. If the map is missing that much material, maybe the map is fine and reality itself has a hole in it. And that's the riddle that's been bothering people ever since. What is the Boötes Void? Let's start with the facts, plain and simple. If you look toward the constellation Boötes, you'll find a massive, roughly spherical region of space about 330 million light-years across that has far fewer galaxies than it should. Astronomers call this place the Boötes Void. To visualize it, you have to picture the cosmic web, which is a massive network of filaments and sheets of galaxies that looks a lot like a three-dimensional sponge. Now, imagine someone reached out and punched a softball-sized bubble right into the middle of that sponge. And that empty bubble is exactly what Boötes looks like. You might wonder how anyone even noticed a hole that big in the first place. Back in the late 1970s and early 80s, research teams were running redshift surveys where they would point a telescope, take spectra, and measure how fast galaxies were moving away to build a 3D map. In certain directions near Boötes, the pencil beams kept returning nothing. And you know what? Astronomers absolutely hate finding nothing. They pushed deeper and widened the beams to find more data, but they just hit more nothing until they finally started to pick up a rim, which was a kind of wall of galaxies skirting a massive emptiness. Get this, if you take a volume of space that big in a normal part of the universe, you'd expect to find on the order of 2,000 galaxies bright enough to show up in those surveys. Inside the Boötes Void, early counts found only about 60 or so, and while later work nudged that number a bit, it's still a massive canyon of underdensity. It isn't completely empty, but the population is shockingly low. Now, we know the universe isn't perfectly smooth. After the Big Bang, tiny ripples in density grew under the pull of gravity, and matter flowed into filaments and nodes while leaving behind these voids. These lower density regions are actually normal, and they usually expand faster than their surroundings. But typical cosmic voids are tens of millions of light-years across, not hundreds. Most of them are irregular and live tucked between walls of matter, but Boötes is oversized, surprisingly round, and incredibly deep. And that combination is what makes people squint. So what exactly do we mean by round in this context? When you slice the sky and stack the redshifts together, Boötes shows up as a broad, near-spherical patch where things are missing. The boundaries aren't perfect because they're a bit lumpy, but you don't see a long, skinny tunnel or some kind of layered gap. You get something that reads like a giant bubble in both projection and depth, and that's weird because the cosmic web is usually made of sharp elbows and flat sheets rather than clean balloons. Let's put some real numbers to this deficit to show the scale. If the average galaxy density in a normal volume is n, this void comes in at something like a few % of n for bright galaxies, though that depends on which catalog you use. That's where that back-of-the-envelope idea of missing 2,000 galaxies comes from. It isn't an exact invoice of every star, but it's an order of magnitude gut check that tells us we should see thousands when we only see dozens. Why does this matter beyond being a cool trivia fact? It matters because our models of how the universe formed, the way dark matter clumps and gas cools, predict a specific distribution of void sizes. If Boötes sits way out in the tail of that distribution, then maybe it's just a rare event. But if it's too big or too clean to be a statistical fluke, then our physics might be missing something huge. Hold on, because we have to consider that biases are real in science. Our own Milky Way blocks parts of the sky with its own dust and stars, which is a problem called the zone of avoidance. But Boötes isn't in that belt, and astronomers have checked the area in multiple wavelengths like optical, infrared, and radio. Dust can hide light, but radio waves sail right through the debris, and the source count still stayed incredibly low. That's why people take this void seriously, because it shows up again and again, no matter what tools we use to look at it. So the central question lands right here. Is the Boötes Void just the extreme end of a natural process, where an underdense region got an early start and kept expanding? Or are we just fooling ourselves with the way we pick and count galaxies? Or, and this is the uncomfortable door number 3, is there some other process that wiped out or prevented normal galaxy growth on a colossal scale? The stakes for this answer aren't small at all. Dark matter models tell us exactly how clumps form from tiny seeds, and if those rules can make a bubble this big, then we learn just how wild the universe can get. If they can't, we're talking about changing the nature of dark matter or revisiting how black holes heat up and clear out gas. Even the way we measure cosmic expansion could be nudged by the fact that we are looking across these massive underdensities. There is a human stake to this story as well. Imagine spending years of your life building a map only to realize there's a giant bite taken out of it. You would triple-check the instrument and swap telescopes, and you'd even ask the colleagues you argued with at the last conference to take a look. The hole doesn't go away, and that's the emotional core here, because scientists don't chase gaps for the drama. They chase them because gaps are where reality tells them to try again. Here's where it gets really interesting. The first radio passes over the Boötes region didn't just fail to find bright galaxies, but they actually reported fewer faint radio sources than other patches of the sky. You'd expect the background to even out when you add up all the tiny emitters like distant active galaxies and star-forming dwarfs. Instead, the radio sky itself seemed to thin out, and that's a clue that puts real pressure on the simple stories. Because if there's less radio noise coming from that direction, this isn't just an optical trick, and the underdensity might cut across populations we thought would smooth everything out. So that's our setup. A round, giant, underdense bubble sitting right where the cosmic web should be busy. It's a discovery that started as a stubborn bit of nothing and grew into a structured absence that is big enough to make any statistician sweat. From here, we have to start testing the stories, whether it's a natural void, hidden matter, or something much stranger, to see which one breaks first. How we found it, the surveys that hit a wall. To understand how we actually stumbled onto this hole, you have to look back at the early days when astronomers were counting galaxies one by one. They weren't actually hunting for a giant void at the time, but were instead trying to build a 3D map of the universe. The way these optical redshift surveys worked was pretty straightforward. You pick targets from photographic plates, feed them into a spectrograph to read their distance, and then stack those distances into a three-dimensional slice of space. In the direction of the Boötes constellation, those stacks kept coming back incredibly thin. It wasn't that the images were blank. There were plenty of candidate galaxies to look at. But when the teams checked for actual objects at the right depths, the galaxies simply weren't where they were supposed to be. Slice after slice, a massive gap started to grow in the data. Here's the thing with optical work. Selection bias is always waiting to bite you. If you only choose the brightest galaxies, you end up biased toward the easy targets, and if you rely too much on color, you might accidentally skip over the dusty or weird ones. Because of that, the pushback from the scientific community came fast. Critics argued that maybe the target list was skewed or the exposure times were just too short to see anything. The teams adjusted their methods by using deeper integrations and different color cuts across wider fields, but the results didn't change. Unknown to them, other groups across town were using their own fiber-fed spectrographs to look at the same spot, and they found the exact same underdensity at the same depth. While all of that was happening, radio astronomers stepped in with a much blunter question. They figured if dust or the glare of nearby stars was hiding something, radio waves wouldn't care at all. They pointed their massive dishes and arrays at the patch, looking for the steady hiss of active galactic nuclei and starburst galaxies that usually light up at centimeter wavelengths. But get this, the counts didn't fill in. You normally expect a specific number of faint radio points in any random square of the sky, but in the Boötes patch, the histogram just sagged. Even after they rechecked their sensitivity maps and cleaned up the data, the deficit held firm. Infrared surveys eventually passed the same test with the same eerie results. If this whole thing had been a trick of old stars swamping out blue light, the mid-infrared should have made those dusty galaxies pop right out. Instead, the surveys that swept the sky at those wavelengths still saw a total desert, save for a few oases on the rim and a handful of lonely galaxies crossing the interior. Even ultraviolet light, which is great at finding young and hot star formation, didn't suddenly reveal some hidden cosmic city. This emptiness wasn't just some single-band illusion. It was looking more real by the minute. People eventually brought up the zone of avoidance because that's the classic gotcha in astronomy. Our own galaxy's disk throws so much dust and stars across our field of view that it erases background galaxies unless you switch to radio or infrared. However, Boötes sits well clear of that messy belt. The star counts are low in that direction, the extinction maps are boring, and the coordinates don't line up with any of the crowded lanes of the Milky Way. It's definitely not our own backyard blocking the shot, so the gap is a real sky feature, not a foreground trick. Data integrity soon became an absolute obsession for the researchers involved. Since catalogs are stitched together from many different nights and detectors, tiny choices in how you flag cosmic rays or set a detection threshold can accidentally carve out artificial holes. To fix this, teams ran null tests where they rotated the sky patch or injected fake galaxies into the raw images to see if the pipeline could still find them. They even masked out bright stars and repeated the entire process from scratch. No matter how hard they tried to break the data, the Boötes hole refused to go away. Reproducibility is the only thing that helps scientists sleep at night, and in this case, the evidence took decades to solidify. The early plates from the 1980s only hinted at a gap, but the multiplex spectrographs of the 90s finally firmed up the discovery. By the time 2000 surveys with automated pipelines arrived, the hole had become boring in the best way possible. Different telescopes and different teams across both hemispheres kept hitting the same wall at the same coordinates. If this were a glitch, it would have to be the most consistent and elaborate glitch in the entire history of sky surveys. Meanwhile, something else was showing up in the radio numbers. When you average the radio sky over thousands of faint sources, the data usually smooths out, which is why radio astronomers love deep fields for their statistical power. In the Boötes region, the faint end of the population looked completely drained. They cross-matched every catalog they had to weed out duplicates and checked their completeness against the noise floor, but the bow and the source count stayed put. This suggests the underdensity isn't just about losing a few bright beacons. The void actually bleeds into the background population of the universe itself. What nobody knew at the time was whether special pockets of space elsewhere could fake this same look. To find out, they pulled comparison patches of sky that matched the same galactic latitude and used similar observing strategies. Those control fields showed exactly what you'd expect for a typical region of the cosmic web, filled with filaments, clumps, and plenty of low-level radio hash. Boötes remained the total outlier. There's still a bit of humility in the margins of this research. It's possible that diffuse, ghostly galaxies are slipping under the detection floor because of surface brightness limits. The count of dwarf galaxies per unit of volume also has some lingering uncertainties, but those are small, nibbling questions compared to the massive gap we're seeing. The bite taken out of Boötes is too clean and too broad, and it shows up in different methods that shouldn't share the same biases. If it's an illusion, it's a massive conspiracy across wavelengths and decades. But if it's real, the story of how it formed has to be much stranger than we thought. The cosmic web versus a spherical nothing. To understand why this hole makes people so nervous, you have to zoom out and look at the big picture. The early universe wasn't perfectly smooth, as it started with tiny ripples in density that were stretched out by inflation. Gravity eventually grabbed those ripples, and over billions of years, matter flowed from the low spots to the high spots. This created long filaments and thick walls, leaving behind the underdense basins we now call voids. That's the cosmic web. It's a tangled, knotted sponge rather than a neat grid. Voids are a standard part of the cosmic deal. They aren't totally empty, but they are very light on matter, meaning galaxies inside them are rare, small, and faint. A typical void might run about 20 to 50 million light-years across. Occasionally, bigger ones show up when smaller voids merge together like bubbles in a sink full of foam. These are usually lopsided and snake between sheets of galaxies, with edges cluttered by the walls where matter finally settled. So why is Boötes such a massive problem for this model? When you map it out, the whole region looks like a bulbous cavity hundreds of millions of light-years across with a fairly smooth interior. It isn't a perfect sphere, but it feels round in a way the cosmic web rarely allows at that kind of scale. You expect voids to look like crumpled, irregular rooms between walls, not like one giant balloon that was blown up inside the lattice. Here's the thing. Our computer simulations of the universe do make voids. If you feed in a starting spectrum of ripples and let dark matter run forward under gravity, you get plenty of empty spaces. But to get something the size and depth of Boötes, you usually need a very specific set of circumstances. You either need a chain of smaller voids so perfectly aligned that they fake a sphere, or you need an initial underdensity that was exceptionally deep right after the Big Bang. Both are possible, but the first is a lucky trick of perspective, and the second is a rare roll of the cosmic dice. Let's talk about the actual depth of this thing. Underdensity is measured as a fraction of the average matter density in the universe. A mild void might sit at about 20% below average, while the deeper ones hit 50% or more. Boötes, at least for the bright galaxies we can see, punches far below those numbers. That doesn't necessarily mean the total mass deficit is that extreme, because galaxies are biased tracers of matter. In low-density regions, galaxy formation is suppressed, so the lack of light can make the whole look even more empty than it actually is. Still, even after you account for that bias, the gap looks incredibly hefty. The roundness of the hole is the second major point of tension. Gravity and cosmic expansion usually make voids more spherical over time as they empty out, but the surroundings usually fight that process. Nearby filaments and walls of matter tug on the voids and distort them into weird shapes. A monster cavity staying relatively round suggests it either had plenty of room to grow without neighbors, or it grew very fast from a uniform low spot. Simulations show you can get that result, but it's a 1% event that rarely looks this clean. Then you have to consider the timing. The universe has had about 13 billion years since the first atoms formed, and void growth is a slow process of matter draining to the edges. To empty out a region this big, you need the clock, the initial conditions, and the neighboring galaxies to all cooperate perfectly. When teams run large simulations with standard dark matter, they do find big voids, but Boötes always sits at the very edge of the distribution. It's the kind of outlier that makes you wonder if you're missing a piece of the puzzle. Now you might say that rare doesn't mean impossible, and you'd be right. The natural void camp leans heavily on that logic. If you stack enough cosmic volumes together, you're eventually going to draw a long straw. To be fair, the rim of Boötes does look like a place where matter piled up into clusters and walls, which is exactly what physics predicts. The handful of small, odd galaxies inside also fits the story that galaxy formation just limps along in these underdense zones. But that's where it gets really interesting. If Boötes is just the extreme end of a known pattern, then other statistics should agree with it. We should see cousin voids nearby that are trending toward that size, and the neighboring filaments should look stretched by the hole's growth. We should even see a weak integrated Sachs, Wolf imprint on the cosmic microwave background as photons cross the underdensity. People have looked for these signs, and while they find hints consistent with a real underdensity, they haven't found a dramatic, smoking gun that explains everything perfectly. The last piece of the puzzle is the centering. Our surveys found a cavity whose center sits almost squarely in the middle of a mapped region. That's partly a selection effect. You only find what you're looking at, but it still raises an eyebrow. If giant, round voids are really that rare, catching one so well-framed feels like an incredible stroke of luck. Luck happens in science, but when you get enough of these lucky alignments, you have to ask if the model itself needs a nudge. That's where the tension stands today. We have a theory that expects a knotted web of small, messy voids, but we're staring at a hole that's too big and too bubble-like for comfort. The natural story can be stretched to fit the data, but it's stretched to the breaking point. To see if that stretch finally snaps, we have to look at the more extreme hypotheses and see if their math can actually carry the weight of what we're seeing. Theory Path 1, an extreme natural void. So let's start with the cleanest explanation. Boötes is a real void, just an extreme one. There are no exotic scars or erased chunks of reality here. It's just the far tail of what gravity can do when it's handed a head start. Picture the early universe laying down a patch of space that was just a little bit lighter than average. It wasn't a crater. It was more like a gentle dip in the landscape. In that dip, matter had less pull, so it drained outward faster than its neighbors, puffing up the interior while stacking material on the rim. If you give that process billions of years to cook, you eventually get a bubble. Here's the mechanism in plain terms. Regions that start out underdense expand a bit faster because there's less gravity to slow them down. That extra expansion lowers the interior density even more, which weakens gravity further, and that speeds up the draining process. It's a feedback loop that hollows out the cavity. Meanwhile, at the edge where all that matter piles up, you grow massive walls and, if you're lucky, entire clusters. That's why the rim of Boötes looks so beefy, and why you still find a few stubborn galaxies inside, because the faucet never actually turns fully off. Supporters of this natural story point to three main lines of evidence. First, the rim is definitely real. Surveys show way more clustering around the boundary, which is exactly what you'd expect if matter had migrated outward over time. Second, the interior isn't perfectly empty. There are a few dozen galaxies in there, often smaller ones with weird shapes, which is consistent with galaxy formation just barely limping along in a starved environment. Third, when you run simulations of massive cosmological volumes, these rare, broad underdensities do actually form, especially when multiple smaller voids merge into one giant complex. Get this, the probability math doesn't say it's impossible, it just says it's rare. Depending on how you define the exact size and depth of the void, estimates put it in the 1 in several hundred to 1 in many thousand range of standard dark matter models. That feels a little uncomfortable, but it's not a total ban. Someone has to win the long shot draw eventually. The real question is whether we're mistaking a stack of smaller, aligned cavities for one giant sphere. If several lumpy voids just happen to sit along our line of sight, they can fake a much rounder shape in space than they actually have. Now, constraints really matter here. A natural void of this size needs initial conditions that weren't totally crazy, but were definitely coordinated. You need a broad, low-amplitude underdensity laid down by the same primordial fluctuations that created everything else in the universe. It also needs neighbors that didn't yank it out of shape. Simulations show that voids do tend to round out as they expand, but the surrounding environment usually fights that. So if Boötes stayed relatively bulbous, it either grew in a very quiet district of the cosmic web, or the initial dip was much wider and smoother than average. Skeptics usually land on three main sticking points. One is the near-spherical symmetry. The cosmic web is usually made of sharp elbows and flat sheets, so neat bubbles are incredibly rare at this scale. 2. The depth implied by the bright galaxy counts looks way too extreme unless galaxy bias is doing some heavy lifting. This means the light might be exaggerating the mass deficit more than usual. 3. There's the timing. Emptying a region this large to this level by now really pushes the growth clock. You can do it, but you need every single dial. The initial amplitude, the environment, and the expansion history, all leaning the same way at the same time. Supporters answer these doubts with fingerprints you can actually test. If Boötes is a natural void, you should see a mild integrated Sachs-Wolf signal, where CMB photons get a tiny energy bump as they cross a giant underdensity in a dark energy era. You should also see weak lensing show less mass projected across the cavity, and galaxy motion should be skirting the hole and streaming toward the walls. Early looks give us hints, but not exactly fireworks. Weak lensing maps trend low, and velocity fields do seem to bend around the emptiness. The CMB imprint is faint if it's there at all, but that's actually normal for a broad, shallow potential. And then there's the life on the inside. Void interiors don't just host fewer galaxies, they seem to pick favorites. You find dwarfs, low surface brightness disks, and gas-rich oddballs, basically the things that struggle to ignite in the thin gas. Finding a handful of these residents fits the model perfectly. Not finding swarms of faint smudges is also fine if feedback and radiation shut down tiny halos in deserts like this. That helps explain why the light makes the gap look much harsher than the actual mass alone would suggest. But here's where it gets interesting for the natural camp, the radio quiet hint. If fewer bright galaxies live inside, you're obviously going to get fewer loud radio cores. But deep radio counts, which average over tons of faint background sources, should usually smooth out. In Boötes, they actually dip. A natural void can handle some of that because underdensity reduces all populations, even the faint ones far in the distance. However, the exact shape and depth of that deficit have to line up with standard models. Some analyses match, others run hot or cold. That tension doesn't kill the natural story, but it raises the stakes. So the most plausible theory in this path goes like this. Boötes is an extreme, but natural underdensity born from a broad initial patch that expanded faster, merged with smaller voids, and stayed round because its neighborhood let it. Galaxy bias makes the light deficit look sharper than the actual hole in mass. That rim clustering is just the expected payback for the emptiness inside. The lensing fingerprints should be there, even if they're faint. And the radio counts are just a stretched version of normal that deeper surveys will eventually resolve. If that stands up, the payoff is big and boring in the best possible way. We don't have to rewrite gravity. We just sharpen our void statistics, fix how light traces mass in cosmic deserts, and learn where our rare line actually sits. And yet, even in this neat picture, one itch remains. That drained radio background. Natural models can tolerate it, but they don't exactly love it. This means, if you're being honest, you have to keep the door cracked for stranger ideas, while you push the measurements even harder. The radio quiet riddle. Here's the thing, if you strip the bright galaxies out of a patch of sky, the radio background shouldn't really care that much. The faint N, which is made of thousands of tiny radio points, usually evens everything out. That's why deep fields look statistically smooth, because if you count long enough, the sky eventually averages out. In Boötes, the average itself seemed lower. It wasn't silent, but it was thinner, almost like the background hiss of the universe got turned down. Start with what we expect to see. Radio astronomers build number counts, which is just a measure of how many sources you get in a unit of sky above a certain brightness. Those counts follow a very specific, known curve once you correct for sensitivity. In most directions, the sea of faint sources swamps any local quirks. Dust doesn't mess with radio much, and the Milky Way's glare drops off once you get away from the center. Because of that, seeing low counts across a big, high-latitude fields should be incredibly rare. Now look at the actual measurement. Teams pointed massive arrays at the Boötes patch and compared it to control fields that matched in latitude and depth. They found significantly fewer faint radio sources than the control curves predicted. It wasn't just the flashy active nuclei either, though those dipped too. It was the garden variety, low, flux points that usually stack into the background. The histogram sagged right where it should have swelled. They checked every boring explanation first. Sensitivity maps can easily fake these kinds of deficits. If the noise is higher in one corner, you're going to miss the faint stuff. To account for this, they built noise maps pixel by pixel and masked out the bad zones. The dip survived. Side lobes from bright sources off camera can also chew holes in the data, so they peeled and cleaned the beams and re-imaged everything with different weightings. They even cross-checked with independent reductions, but the gap stayed put. Catalog stitching can double count or drop sources, so they cross-matched to external catalogs and ran blind injections. They sprinkled fake point sources into the raw data to see what the pipeline recovered, and while the recovery rates matched expectations, the sky itself did not. Get this, the frequency actually helps us here. If absorption or scattering were damping the signals, you'd expect a hit that changes depending on the frequency. At the centimeter wavelengths used for this kind of work, the counts in Boötes were low across multiple bands that should behave differently if there was a local fog in the way. The curves shifted down in rough lockstep, which smells a lot more like fewer sources than just muted ones. But wait, could it just be cosmic variance? On small patches of sky, the universe is lumpy and number counts wobble all the time. That excuse starts to fade when the patch is this large, and the underdensity spans hundreds of millions of light years in depth. Averaging along that long path usually brings you back to a typical number. Here, the long integral looked completely drained. Statistically, the deviation cleared the just noise bar in several different analyses, though nobody is calling it proof of something exotic just yet. So what does a lower radio density actually mean? First pass is that it's consistent with a real mass underdensity that suppresses all kinds of galaxies, both bright and faint. There are simply fewer radio emitters along that line of sight. That fits the natural void story, but it comes with a note pinned to the door. The faint end may be more biased than we assumed, or the void could be broader in its true three-dimensional reach than the spherical picture suggests. Here, that's where it gets interesting. The depth of the radio dip hints that it's not just the bright beacons that are missing. The skinny tail, things like dwarf starbursts and low luminosity active nuclei, might be suppressed more than our models expect in these kinds of deserts. That pushes on our recipes for how galaxies form. Maybe the heating of the universe shut down gas cooling in tiny halos more efficiently there. Or maybe feedback from early black holes sterilized these patches longer than we thought. Or perhaps the mass underdensity is just stronger than the light tracers imply. And then there's the edge case that nobody really loves to say out loud. Could something be damping the signals instead of just removing the sources? At these wavelengths, the universe is usually pretty kind. Something like absorption or scattering by hot plasma on massive scales would need conditions we just don't see anywhere else. Faraday effects twist polarization, but they don't change the counts. A foreground screen big enough and tuned enough to dim a wideband across such a huge area would leave other fingerprints. People looked for those, like temperature steps in the microwave background or weird rotation measures, and they didn't find a smoking gun. So the conservative reading wins for now. The radio sky looks thin because the space itself is thin. There are fewer halos, fewer galaxies, and fewer engines to make radio waves. The implication is sharp, though. If the underdensity bleeds into even the faintest populations, then it all averages out. Comfort blanket doesn't always hold at this scale. That forces us to build tighter models of how light traces mass in voids, and it sets the stage for door number 2. What if some of the mass is actually there, but it's just dark enough that our optical, infrared, and radio telescopes keep missing it? Theory Path 2, Hidden Matter in the Dark Web. So here is door number 2. What if the mass isn't actually missing, but it's just hiding? I don't mean a camera trick, but rather the possibility that most of the matter in this region simply never lit up. You can think of it like a massive scaffolding of dark matter halos stretching through the void, where galaxy formation was so throttled that light barely exists to mark the spot. On a traditional map, the area reads as empty, but in terms of gravity, it still tugs on everything around it. Let's start with the basic idea behind this. In our standard model of cold dark matter, these halos should form everywhere, even in low-density areas, though they would typically be smaller and fewer in number. If the gas cooling process stalls out or if stellar feedback kicks too hard, those halos fail to grow into bright, visible galaxies. Warm dark matter could make this even more extreme because its thermal motion smears out the tiny seeds of structure, creating a skeleton that is smoother and much dimmer. Either way, you end up with a dark web where the mass is physically present, but the light has completely deserted you. How do you actually see a structure that refuses to show itself? You have to let gravity do the talking, and weak gravitational lensing is the first real test for this theory. It is a subtle effect where background galaxies appear slightly sheared by the mass sitting in front of them. If you stack enough of those shapes across the Boötes line of sight, you can map out the projected mass regardless of how much light is there. A true physical deficit of matter should show a massive dip, but a hidden mass void might look less empty in a lensing map than it does in a galaxy count. Then we have the CMB lensing to consider, which uses the cosmic microwave background as one giant, ancient backlight. Mass along the path nudges those photons as they travel, and by cross-correlating these lensing maps with the footprint of the void, we can test if the gravitational potential is as hollow as the galaxy map suggests. Results are mixed. Some analyses hint at a modest underdensity that fits a real void but not a total, gaping hole. So far there is no smoking gun, signal showing tons of hidden mass, meaning if a dark web lives there, it isn't dense enough to cancel out the light deficit. Velocity flows provide the next big fingerprint for us to examine. Galaxies don't just ride along with the expansion of the universe. They naturally drift toward mass and away from empty spaces. If Boötes truly holds less mass, the surrounding galaxies should show peculiar motions that skirt around the cavity and stream along filaments toward the walls. By mapping those flows, we can weigh the void without ever asking it to glow. Observers have seen hints of that specific bend, with velocities curving around the gap, which points toward an honest underdensity in mass even if the exact depth is still being debated. Now we have to look at the predictions. If hidden mass fills this void more than the light implies, you would expect to see a much smoother structure on a small scale. This means we should find fewer dwarf galaxies than standard simulations predict, especially the faint, gas-rich ones that usually pop up in these models. The slope of the luminosity function inside the void should be flatter, showing a lack of tiny galaxies compared to denser regions of space. Star formation rates should also skew low because neutral gas reservoirs might have been heated up too early to collapse. When we look at the data, that is largely what we see. Not many dwarfs and very little radioactivity. The place where this theory takes a hit is in the sheer amplitude of the emptiness. To reconcile the feeling of 2,000 missing galaxies with a lensing signal that isn't a total crater, you need galaxy bias to be working overtime. This means light would have to be a very poor tracer of mass in cosmic deserts, which is actually quite plausible. In deep underdensities, the bias factor tends to climb because galaxies become rare markers of a stretched-out mass field. However, there is a limit to how much bias can hide, and current lensing data suggests the mass deficit is a real physical feature, rather than a magic trick played by dead galaxies. Warm dark matter is often brought up because it naturally smooths out the tiniest lumps of matter and starves dwarf galaxies of the fuel they need. If you dial the free streaming scale just right, you can cut down the number of small halos in voids more effectively than in dense regions. This would flatten the galaxy counts and create that dark desert look without requiring a massive hole in the underlying matter. But here is the problem. Other data from the Lyman Alpha forest and satellite counts already pin warm dark matter into a very tight corner. If you push it far enough to fix the Boötes problem, you end up breaking everything else, so any warmish tweak would have to be very mild. What about the idea of self-interacting dark matter? If these dark matter particles occasionally bump into each other, the cores of their halos could puff up and make galaxy formation much tougher in low-pressure environments. That could potentially thin out the interiors of voids without wrecking the structure of massive galaxy clusters. The telltale sign would be altered halo profiles on the rim and strange core sizes in the few galaxies that actually live inside. People are definitely looking for this, but we haven't found a clear aha moment tied specifically to Boötes just yet. But get this, there is a much cleaner and more conservative way to look at this. We can keep our standard cold dark matter and simply accept that there is a genuine underdensity of mass, even if it isn't as savage as the light suggests. If you add strong environmental bias, where gas cooling and star ignition stall out in thin regions, the halos simply stay dark. This predicts three things we can check very soon. Lensing across the void will be low but not zero. The rim will host more efficient star-forming halos than the interior, and the faint galaxy counts will stay flat even after we use our best telescopes. So far, the evidence seems to lean in that direction because lensing hints at an underdensity, and no hidden mass surplus has arrived to save the day. It doesn't solve the entire radio dip, but it takes a significant bite out of the mystery by admitting that the faintest engines are missing because their halos never lit up. If that turns out to be true, the stakes for our models get much higher. It means our recipes for galaxy formation, things like cooling thresholds and feedback strengths, need much more sensitive, environment-aware dials. If we get those wrong, our maps will continue to lie to us every time we try to turn light into mass. Midpoint reversal, the probability cliff. This is the part where the ground starts to tilt under our feet. Up until now, we could tell ourselves that this void was extreme but still a natural part of the universe. Then you run the actual odds, and things get uncomfortable. Teams have taken massive cosmological simulations with billions of particles and standard rules to ask a very blunt question. How often does a cavity this size and this round actually show up? The results are not exactly encouraging. Depending on how you define the boundaries, you are looking at probability tails so thin they are effectively cliffs. Here is the thing. The answer changes depending on how you draw the circle, but the overall trend stays the same. You might find a void like this once in every few hundred simulations if you are being generous. If you are strict about the size, the depth, and the roundness all happening at once, the odds drop to 1 in tens of thousands. This isn't just the chance that a void exists somewhere in the infinite universe, but the chance that a survey like ours would land on one this clean and well-centered. That specific conditioning shrinks our comfort zone significantly. We have reached a major crossroads here. Either we are the incredibly lucky winners of a cosmic raffle, which is possible since someone has to be, or something about how we see the universe is fundamentally off. There is a name for that first option, and it's called selection bias. We tend to point our telescopes where it is convenient, and we publish the things that are most interesting. That can easily tilt our perception, and maybe there are other big underdensities lurking in patches we haven't mapped yet, making us overvalue this one because it's framed so perfectly. But wait, there is also a related problem where we live in a lumpy universe and inevitably build grand stories around the lumps closest to us. Our cosmic neighborhood features the local hole debate, strange bulk flows, and now this giant void sitting right in our sightline. If you stack all of those anomalies together, you can accidentally convince yourself the universe is much stranger than it actually is. The probability cliff we are looking at might just be a mirage built from a bunch of stitched-together coincidences. However, there is some serious pushback to that idea. Independent teams using different instruments over several decades keep seeing the exact same gap in the data. The radio source counts dip, the infrared surveys stay sparse, and the lensing trends always come back low. If this were just a case of us pattern matching random noise, those signals wouldn't line up across so many different wavelengths and methods. The cliff might be very real, which would mean our model's predictions are thinner than the data demands, or perhaps our choices for things like small-scale power need a nudge. This is our midpoint reversal, the exact moment where the story we started with stops being the safest bet. Up to this point, the idea of an extreme natural void felt like the most logical explanation in the room. Now the math is stepping in to ask why this specific hole, with this specific roundness, landed right in our lap without breaking the laws of probability. If you can't answer that, you either have to find more voids like it to prove it's common, or you have to expand your theory to explain why it's there. So we have to reframe the core question of this whole mystery. It isn't just about why a giant void exists, because we already know that voids are a standard part of the cosmic web. The real question is why this specific void is so clean and so quiet in the radio spectrum. That level of precision is what beats our general explanations. It forces us to look for mechanisms that can carve out these massive spaces more efficiently, or perhaps leave behind scars that light would notice even if the mass doesn't. That is the door creaking open to our third path. We aren't talking about deleted space anymore, but the idea that early universe physics could have planted a causal defect or a bubble with slightly different rules. If that sounds a bit wild to you, that's actually a good thing. The next step is to make that idea feel boring by looking for the fingerprints, the edges, the temperature steps, and the asymmetries that will either prove it or kill it. Because when you are standing at the edge of a probability cliff, you really need some guardrails. Theory Path 3, the erased patch hypothesis. So door number 3 isn't about someone manually deleting space. It's actually a bit cleaner than that. The idea here is that something in the very early universe changed the rules inside this specific patch, so normal galaxies never really had a fair shot at growing. Think of these as causal scars, little imperfections left over from when the universe was cooling down, or maybe bubbles where the vacuum state shifted just a tiny bit. It isn't magic, it's just physics leaving a permanent bruise on the fabric of space. We can start by looking at topological defects. When the universe cooled down through different phases, various fields had to pick a direction, sort of like how iron domains choose their magnetic orientation. When those different domains tried to stitch together, they could trap seams in between them, creating things like cosmic strings or textures. If a large, gentle defect passed through the area that eventually became Boötes, it could have slowed down the growth of matter over a massive zone. This would keep the interior starved of material while piling all that extra mass into a thick rim around the edge. You'd be able to spot this by looking for a faint, circular temperature pattern in the microwave background that lines up perfectly with the void. Then you have the vacuum bubble theory, which sounds like sci-fi, but is actually grounded in how space behaves. During the era of inflation, space can tunnel between slightly different states of energy. If a bubble of not quite our vacuum started growing and brushed against our region, its wall would have swept through and changed the growth rate of everything inside that patch. You don't need a whole pocket universe for this to work, because even a tiny change in the speed of sound or energy potential would mean fewer galaxies crossing the finish line to actually form. If this happened, we'd see a circular edge on the sky with a very subtle temperature jump, along with gravity pulling light in a very specific, lopsided way across that boundary. There's a third possibility that's less exotic on paper, but absolutely wild when you think about the scale. Imagine a swarm of ancient, massive black holes or hyperactive stars that went totally berserk in the early universe. They could have bathed this entire region in so much radiation and heat that the gas simply couldn't cool down enough to form stars for a very long time. This would effectively sterilize hundreds of millions of light years, empty, leaving gas eventually collected at the edges to form a rim. The problem is the energy bill, because to keep a region that big hot for that long, you need a massive amount of power. We've looked for the receipts for this, like shock-heated X-ray gas or metal signatures in the sky. But so far, nothing is screaming blast wave across the Boötes region. So what would it actually take for any of these ideas to be more than just a cool story? It all comes down to the edges. You need a boundary that you can actually draw on a map. For a defect or a bubble, that edge should be much cleaner and more circular than a random gap in the cosmic web. We need to see temperature steps in the microwave background that stay consistent across every frequency we check. We'd also need to see the gravity of the area acting like a shallow basin, with galaxies and light bending around the boundary in a way that normal filaments can't explain. Now we have to look at the counter-arguments, because science is all about trying to prove yourself wrong. If a topological defect left this patch empty, we really should be seeing its cousins all over the rest of the sky. These textures don't usually just happen once and then disappear forever. While some studies flagged a few candidates, like the famous cold spot in the constellation Eridanus, most of those turned out to be ordinary voids or just statistical flukes. The latest data from the Planck satellite has put some pretty tight limits on how many of these defects are allowed to exist, which really squeezes this theory into a corner. The vacuum bubble idea faces a similar uphill battle. When researchers searched the cosmic microwave background for the telltale signs of bubble collisions, they didn't find a clear population of them. A single, very weak bubble might have slipped through the cracks, but it has to be in a very narrow Goldilocks zone. It needs to be weak enough to hide from our telescopes, but just strong enough to have cleared out this massive hole in space. That's a pretty tough balance to maintain, especially since we haven't seen the specific light patterns those collisions should leave behind. As for the idea of berserk feedback from stars or black holes, the lack of a giant X-ray shell is a major red flag. You can try to argue that the gas is too thin to see, but if it's that thin, it wouldn't have been strong enough to stop galaxies from forming in the first place. Plus, when we look at the chemical fingerprints in the light passing through Boötes, we don't see the overcooked metals you'd expect from a massive explosion. The interior of the void looks remarkably quiet and normal, rather than like a cosmic crime scene. But that's where it gets interesting, because we can hunt for these fingerprints without having to go all in on one theory. We can use microwave maps to look for broad, cold patches that stay put when we rotate the data. We can use weak lensing to weigh the entire region and see if there's a hidden rim of mass. We can even use deep radio surveys to see if there are tiny, faint galaxies hiding in the dark. Each one of these tests either brings us closer to some erased patch, physics, or tells us that this is just a big, boring void doing exactly what voids do. So far, the sky is acting like a total skeptic. We see hints of the underdensity across different wavelengths, but no crisp, exotic scar has jumped out at us yet. That doesn't necessarily kill the idea that early physics left a mark on Boötes, but it does mean the evidence isn't demanding a wild explanation just yet. At the end of the day, the responsible move is to take these wild ideas and turn them into hard measurements. We have to map the edges, check the numbers, and let the universe call our bluff. Evidence hunt, multi-wavelength fingerprints. If this void is truly as empty as it looks, then gravity and light should both be telling us the same story. To find out, we have to go through the sky wavelength by wavelength and ask it to show its hand. We start with the oldest light in existence, the cosmic microwave background. These photons have been traveling for billions of years, and they feel every single hill and hollow in the gravitational landscape. When they pass through a giant empty space, they get a tiny nudge in energy, which is a subtle effect that we can actually test for. Researchers took the footprint of the Boötes Void and compared it to other parts of the sky using data from the Planck satellite. Here's the thing. The patch looks a little bit colder than the surrounding areas, and that cold spot lines up reasonably well with the void's outline. It isn't a perfect bold or a dramatic disk, but it's a wide, shallow sag in temperature, which is what you'd expect from a giant underdensity via the integrated Sachs-Wolf effect. When they rotated the map to check for errors, the signal behaved as expected. It's not a smoking gun, but it's a consistent sign that the void is physically there. Next, we look at X-rays. If the void was just missing galaxies but was still full of hot gas, we'd see it glowing in X-ray telescopes, or we'd see bright clusters marking the edges like a neon sign. But when we look at the catalogs, the interior of Boötes is incredibly quiet. There are no bright clusters puncturing the center, and no massive surges of background radiation. We do see some groups of galaxies sitting right on the boundary wall, which is normal, but there's no giant shock wave or bubble wall. It just looks like a place where matter simply didn't want to go. If we slide over to ultraviolet and infrared light, we're looking at the bookends of how stars are born. Young stars shine bright in UV, while dusty, growing galaxies hide and glow in the infrared. If there were a bunch of hidden cities of galaxies tucked behind clouds of dust, the infrared telescopes would have found them by now. But they didn't. The wide sweeps of the sky show the same desert-like emptiness inside the void, with only a few lonely islands of galaxies that manage to grow in the thin gas. Star formation isn't hiding behind a veil. It's just genuinely rare in this part of the universe. We already know that radio signals are thin in this area, but radio telescopes also help us test the edges of the void. By mapping out faint active black holes in star-forming regions, we can see the sea level of the universe drop as we move inside the hole. Crucially, that drop-off is smooth and gradual. There isn't an abrupt cliff or a weird filter that's blocking the light. Everything shifts together, which tells us that there are simply fewer engines running in the engine room, rather than someone putting a muffler on the exhaust. The real adult in the room for this investigation is gravitational lensing, because it weighs mass without needing it to shine. By looking at how the shapes of distant galaxies are warped by gravity, we can create a mass map of the Boötes footprint. The map that comes back isn't a total crater, but it is significantly lower than the average density of the universe. There isn't a secret pile of dark matter hiding inside to cancel out the missing light. The mass is honestly missing, though perhaps not quite as severely as the galaxy counts make it seem. This fits the idea that emptiness gets exaggerated in places where galaxies have a hard time forming. While all of that was being measured, something else was showing up in the way galaxies move. Galaxies near the edge of the void don't just fly straight away from us with the expansion of the universe. They actually drift sideways. When we map out these peculiar velocities, we can see the streamlines of motion bending and skirting around the hollow space. It's almost like a whirlpool, where the flow of matter respects the empty cavity and funnels toward the walls. This is like a dynamical handshake with our gravity maps, confirming that there's less mass inside and more on the edge. There is one last check we can do called the Sunyaev-Zeldovich effect, which happens when hot electrons in galaxy clusters kick light up to higher energies. If we stack all these signals together, the interior of the void should be much quieter than the rest of space because there aren't many massive clusters there. And that's exactly what the data shows. A total poverty of hot, high-pressure gas inside the hole, with only modest bumps along the rim where we already knew clusters were sitting. There's no giant ring of fire or pressure wave, just a lot of nothing. So what's the verdict when you stack all these different bands of light together? Every careful test points the same way. The Boötes void is a real underdensity in both mass and light. The microwave background shows a faint ISW-like nudge. The X-rays show a lack of hot structures, and the UV and infrared confirm that it's a star formation desert. The radio counts are thin, the lensing shows a dip in mass, and the galaxy flows curve around the gap. We don't see any exotic scars or sharp edges that scream alien physics, but we do see a very consistent hole. That's really the main point here. The sky doesn't actually need a special effect or a wild theory to explain why Boötes exists. It just requires us to have a little more patience and better tools to see the faint signals. This is why we keep pushing our measurements to the absolute limit. We have to keep asking the boring questions to make sure that no pipeline error or data glitch has faked a hole this big and this consistent. Measurement gauntlet, could it be an illusion? If you want to kill a scientific result, you don't just argue with the person who found it. You try to recreate the whole thing and break it yourself. That is exactly the kind of gauntlet the Boötes Void had to run. Researchers started with the hardware because radio arrays and optical cameras are full of weird quirks like dynamic range limits or side lobes around bright light sources. Any one of those technical glitches could, in theory, carve a fake hole into the data. To rule this out, teams mapped the noise instead of just the sky, using pixel-by-pixel sensitivity grids to flag hot and cold zones. They masked the worst areas and reran their source extraction with multiple different thresholds. And while the deficit shrank a tiny bit, the overall result didn't flip. Confusion noise is a classic problem in radio astronomy, where too many faint smudges overlap, until you start mistaking blended blobs for single sources. This makes you lose the weakest signals, so the researchers pushed the resolution higher and changed their weighting schemes to see if the hole disappeared. They also did the boring hero work of cross-checking beam models and re-imaging the entire field from scratch to be absolutely sure. If confusion had been eating the faint sources in Boötes more than in other control fields, the counts would have rebounded after this deep cleaning. Instead, the curve stayed low by a similar fraction no matter which processing choices the teams made. Optical pipelines were next on the hot seat because surface brightness limits can be incredibly sneaky. A galaxy can be bright in terms of its total light, but spread so thin across the sky that it falls right under the detection floor. To see if they were missing these ghostly disks, teams injected synthetic galaxies, basically fake sources with different sizes and brightness levels, directly into the raw frames. They ran the full reduction process to see what fraction of those fake galaxies came back, and the recovery rates matched expectations perfectly inside the Boötes footprint. If the software were punishing diffuse sources specifically in this region, the injection test would have caught it, but it didn't. Catalog stitching can also create problems where different fields meet, especially since small shifts or masked halos around bright stars can chew away at the object counts. To test this, the researchers literally rotated the sky by taking the Boötes mask and spinning it to a clean patch of sky with a similar galactic latitude. The holes didn't follow the mask. They stayed exactly where they were in the original data, which proved the void wasn't a software artifact. They even randomized the masks and checked that the number of sources lost near bright stars matched their mathematical models, and the deficit held strong even far away from any problematic star halos. Selection functions are another way things can go wrong because if your target list is built from specific color cuts, you might quietly veto oddball galaxies without realizing it. Teams decided to redo their target selection with much looser rules, while others used magnitude-limited lists that had no color bias at all. Fiber assignment can also be an issue because tiling algorithms might dodge dense patches or even thin ones if the math expects a certain number of neighbors. They varied their tiling strategies and compared the results to slit surveys that don't use the same fiber geometry. Yet every different selection method showed the same underdensity and redshift space. Null tests are what scientists use to save themselves from their own biases, and one favorite method involves synthetic injections at the catalog level. They sprinkled fake point sources with realistic brightness and positions into the radio images to see if the pipeline could recover the right counts against the background noise. In the Boötes region, the completeness curves for these recovered sources matched the control fields within the standard error bars. This confirmed that the sky itself was the outlier, not the software used to map it, and that the void was a physical reality rather than a digital ghost. Community replication is the ultimate test because you don't get the same dropout pattern across different teams unless the cosmos is actually cooperating. Across town, other researchers with different telescopes pointed their instruments at the exact same coordinates to see what they could find. They used wide-field radio mosaics from different arrays and mid-infrared sweeps from various satellites, along with optical redshifts from both hemispheres. Independent reductions and calibrations performed decades apart all came back with the same hole. And if this is somehow an artifact, it is a conspiracy with a very long memory. The last refuge for skeptics is the idea that the faintest stuff might still be hiding below our current detection floors. Low surface brightness galaxies and ultra-diffuse dwarfs could theoretically fill in the interior counts if we had infinite exposure time and perfect sky subtraction. However, even if a hidden population is lurking in the dark, the lensing and velocity fields already tell us that the total mass in that region is low. You can add a few wisps of light here and there, but that won't change the answer gravity is giving us. The uncertainty at the faint end of the scale is real, and it softens the drama a bit, but it doesn't erase the cavity. Instrumental ghosts always have specific tells that researchers can look for, such as absorption screens that would only show up at certain frequencies. The radio dip in Boötes shifts in lockstep across different bands, and pipeline masks would usually align with the geometry of the field, but this deficit ignores tile edges entirely. Milky Way foregrounds would track with dust extinction, yet Boötes sits in a very clean part of the sky. Each potential illusion predicts a specific kind of scar that we can measure, and those scars simply don't line up with the outline of the void. The final verdict from this gauntlet is exactly what you'd expect from careful work. It is boring and it is strong. Dynamic range limits don't explain the gap, confusion doesn't account for it, and neither do selection tweaks or stitching quirks. Null tests don't budge the result, and every replication keeps finding the same thing, which means we are officially out of excuses. Residual uncertainties still exist at the margins, like those ultra-diffuse ghosts or the faintest radio signals, but they only nibble at the edges of the problem. If the map shows a hole after you try to break it a dozen different ways, you are probably just staring at a hole. What this breaks if it's real? If the Boötes hole is real and as deep as the data suggests, it knocks several major parts of our understanding sideways. First, we have to talk about timing because structure formation in the universe follows a very specific clock. Tiny ripples from the early universe grow into halos, then galaxies, and eventually massive clusters, while voids grow much slower as matter drains out of them. A cavity this large and this round pushes that clock to its absolute limit, and if standard growth models can't empty a region this wide by now, something is wrong. Either our initial conditions are off or the history of how things grow bends in a way we didn't expect. Next, our dark matter models have to face a serious hit test. Cold dark matter usually makes lots of small seeds that merge together over time, while warm dark matter erases those tiny seeds and smooths out the cosmic web. The deficit of both bright and faint galaxies in Boötes tells us a lot about how those seeds light up in the middle of cosmic deserts. If the hole is too clean for standard models, we might be forced to allow for a much stronger environmental bias, or even tweak the microphysics of dark matter itself. The problem is that if you push those tweaks too far, you break other measurements like the Lyman alpha forest. Galaxy bias, the idea of how light traces mass, is also landing right in the crosshairs of this discovery. We have spent decades building cosmology on the assumption that galaxy counts are a reliable map for where the mass is located. In deep voids, that shortcut can turn out to be a lie, because if halos don't form stars efficiently in thin gas, the light will underestimate the mass by a huge margin. Boötes forces us to calibrate our bias models in the exact places where they are weakest, such as low density and low metallicity environments. If we get that wrong, we will misread any survey that relies on galaxy statistics to weigh the universe. There is also a debate that astronomers have late at night regarding local expansion and the Hubble rate. If you are looking across a massive underdensity, your measured expansion rate can tilt because fewer gravitating masses allow that local patch to expand a bit faster. Some researchers have tested whether local underdensities could ease the Hubble tension, the mismatch between early universe predictions and nearby distance measurements. While Boötes isn't in our immediate neighborhood, it serves as a clean laboratory for this effect. And if underdensities this large are common, they could bias supernova samples. The integrated Sachs Wolf signal is another piece of the puzzle that gets complicated by a giant void. We use these signals to check for the fingerprints of dark energy, but a massive underdensity can act as both a test and a trap for our models. It is a test because the way its gravitational potential decays can tell us about the dark energy era, but it's a trap if we misestimate the mass profile. Boötes is essentially telling us that we need to calibrate our void physics very carefully, or our constraints on dark energy will start to drift away from reality. Gravitational lensing pipelines also take some collateral damage here, because we usually trust that stacking lensing over many sightlines will wash out any weirdness. A large, honest hole shifts the entire baseline for these measurements, and convergence maps over voids are supposed to help anchor our mass calibrations. If the faint-end galaxy population is more suppressed than we thought, it can skew the redshift distributions and noise models we use for weak lensing. This bleeds into our analyses of cosmic shear and structure growth, meaning our models need to learn how to breathe with the emptiest rooms in the cosmic web. When it comes to modified gravity, voids are actually where alternative theories like to show off because certain effects get stronger in low-density areas. If Boötes holds less mass than the light implies, and if the velocities of galaxies around it bend more than standard gravity predicts, that is a quiet invitation to look at new models. So far, the data stays close enough to general relativity to keep those alternative ideas on a leash, but a well-weighed supervoid is a powerful lever. If you pull it carefully, you either tighten the screws on our current understanding, or you finally find some slack in the system. There is also a bit of a cultural shock involved in how comfortable we have become with our cosmic maps. We like to tell ourselves that the cosmic web is statistically even when you look at large enough scales, but then a clean hole shows up and refuses to go away. This doesn't mean the whole idea of a uniform universe has failed, but it does mean the path to that uniformity runs through deserts that can fool a quick look. Boötes breaks the habit of assuming every empty patch is just a mistake until proven otherwise, and it flips the burden of proof back onto the skeptics. Finally, we have to look at the philosophy under all this data. We often mistake our maps for laws of nature when those maps look smooth and predictable, but an anomaly like this forces us to separate the two. If a single void can push our timing, stress our dark matter theories, and expose flaws in our bias models, then our precision depends on how we handle the weird parts. Boötes won't rewrite the entire history of the Big Bang, but it sharpens the parts of the story we usually rush past. If we don't tighten those details, every new survey will just give us prettier pictures that hide the same old blind spots. Working model, the plausible synthesis. So here is a model you can actually live with today without feeling like you have to break the laws of physics to make it work. The Boötes void is definitely real, and it is definitely extreme, but it still fits inside the world of standard physics. You start with a broad, honest dip in mass that is a bit shallower than the lack of light suggests, and it probably started as a gentle, wide ripple in the early universe. Over billions of years, this area expanded faster than everything around it, merged a whole chain of smaller voids together, and rounded out because the neighboring galaxies didn't tug on it too hard. That gives you that giant bubble feel without needing a scientific miracle to explain it. Now, you have to layer in the fact that galaxies are much pickier about where they grow than our quick models usually assume. In these thin stretches of gas, the dark matter halos really struggle to get anything going. The cooling stalls out, radiation hits them earlier, and any feedback from stars kicks much harder because there is less mass to hold things together. The result is that the same amount of mass produces way fewer lights, which is exactly why the galaxy counts seem to crash much harder than the gravity measurements do. The light is basically exaggerating how empty the place is, even though gravity still confirms the area is low. You can actually measure that gap because the gravity maps show a soft depression, while the galaxy counts look like a total canyon. And that difference is just the bias of the galaxies talking to us. If you want to get specific, you can add one small physics twist that doesn't ruin any other data we have. If you use slightly less small-scale power than the most aggressive dark matter models, which is still well within the margin of error, you can trim the number of tiny halos inside these voids. This flattens out the population of faint galaxies and deepens that dark desert look without having to invent new types of dark matter that would mess up our other observations. Think of it more like nudging the dials on a machine, rather than trying to swap the whole engine out for a new one. When you put all those pieces together, you start getting some very clean predictions about what we should find. The rim of the void should be crowded compared to the empty interior, with groups and clusters of galaxies stitched together into a thick, protective shell. Inside that shell, you will still find a handful of stubborn residents like gas-rich dwarf galaxies or low-surface brightness disks, which is fewer than the basic models predict, but it is definitely not zero. The gravity maps should show a broad, low bowl with a gentle shoulder at the edge, rather than a sharp, jagged wall. You should also see a faint imprint on the cosmic microwave background, appearing as a low, wide sag in the maps that stays consistent across different frequencies. Even the radio galaxy count should dip across the board, meaning there are simply fewer engines running in there rather than the engines just being muffled. This working view also tells us exactly what we should not see if the model is correct. We shouldn't see any crisp, circular temperature steps in the microwave background that would signal a defect in space-time. There shouldn't be a ring where mass is missing on the inside but overabundant just outside in a tight, cramped shell. We also shouldn't find any giant X-ray shocks that would suggest some titanic explosion happened in the past. Instead, what you get is a boring, consistent lack of hot gas and loud engines in the middle, with some ordinary clusters marking the boundary. The reason this earns the plausible tag is that it threads the needle through all the evidence we already have on the table. Gravity hints at a low mass but nothing catastrophic, while the way galaxies move shows them bending around the hole. Our infrared and ultraviolet telescopes see a total desert for star formation, and the radio data dips without showing any weird frequency glitches. Even the background radiation maps nod in the right direction, if only barely. Nothing here demands that we invent new particles or cosmic scars, but it also doesn't let us keep pretending that these voids are just small, messy footnotes in a textbook. This model also leaves room for that nagging radio data, because if the faintest galaxies are more suppressed than we thought, that is a problem with how galaxies form, not a problem with gravity itself. It forces us to realize that the environment matters when it comes to how stars are born and how they die. Because this is a working model, it comes with some very clear tests that could prove it wrong in the near future. First, we need deeper radio sweeps to see if the faint galaxies start showing up, and the data should show a smooth rise toward the rim rather than a sudden jump. Wide-field gravity maps should find that soft, bowl-shaped dip with a mild shoulder and no surprise humps of mass hiding inside. When we look at the dwarf galaxies through a spectrograph, we should see a flatter population inside the void, and a much more normal, steeper population along the edge. The signals in the background radiation should stay broad and faint even when we shift our maps around. Finally, the maps of how galaxies move should show them flowing toward the walls at speeds that match the mass deficit we measured with gravity. On the flip side, here is how the model dies. If we find a bunch of hidden mass inside the void that our gravity maps missed, this whole synthesis breaks apart. If a sharp, circular edge shows up in the microwave background that lines up perfectly with the void, then you are looking at a cosmic defect instead of a gentle dip. If deep infrared surveys reveal a rich population of dusty galaxies that we simply missed before, then the bias of the light did all the work, and we would have to explain why gravity didn't notice them. If our X-ray telescopes find a massive shell of pressure, then the idea that there was no exotic feedback fails completely. Here is the thing. The real value here isn't just about solving the mystery of Boötes. It is about giving the entire field of cosmology a much cleaner playbook for how to handle voids. We can learn to calibrate our bias where it hurts the most and tie these gravity bowls to the light deserts using models that actually care about the environment. We can use this one supervoid as a test bench for our pipelines and our reconstructions of how galaxies move through space. If this synthesis holds up, we get to keep our current model of dark matter while simply upgrading our recipes for how galaxies form in the thinnest places in the universe. But if it cracks, we will know exactly where to look for the missing physics, whether it is at the edge of a map or in a background signal that finally refuses to play nice. The next 5 experiments that decided. So here is how we stop the arguing and let the sky choose the winner. We have 5 moves, each with a very clear yes or no answer, and all of them are aimed directly at the Boötes footprint. First, we need a deep, low-frequency radio survey that goes much further than just another quick pass. We need to go wide and faint at about 150 to 600 megahertz, with long dwell times to see what is really hiding there. We need a single, massive mosaic centered on the void that rolls well past the rim so we can see the transition. The stakes are simple because if the dip in radio counts is just because the bright engines are missing, the faint ones should start showing up as we look deeper. If the entire population is suppressed, the whole curve will shift down together across every category, and the profile will rise smoothly toward the rim. By mapping these counts and comparing them to the areas outside the void, we can finally decide if we are just seeing fewer engines or if something else is going on. Second, we need a wide-field gravity map that covers the entire void and the surrounding rims. We don't need pretty pictures for this. We just need stable data and a clear look at how the light from distant galaxies is being bent. This is the ultimate test because gravity weighs mass without caring whether that mass actually shines or stays dark. We can stack the data in concentric rings starting from the center and moving out past the wall to look for that specific shoulder shape at the rim. If we find a broad, low bowl with a gentle rise at the edge, it nails the coffin on the idea that this is a real mass hole. But if the profile is flat or noisy, or if we find a surprise bump of mass inside, we have to rethink everything we thought we knew about galaxy bias. Third, we need to do a spectroscopic sweep of all the dwarf galaxy candidates to lock down the population counts. The real truth of the interior lies in the ghosts, like those low surface brightness disks and gas-rich dwarfs that are incredibly hard to see. Taking photos and guessing doesn't work anymore. We need spectra to be sure. If these tiny halos form stars anyway, they will fill the desert with whispers that we have been missing this whole time. By using advanced spectrographs to get secure distances and star formation flags, we can split the samples between the deep interior and the rim. If the population is flatter inside and gets steeper toward the wall, it proves that the environment is stopping galaxies from forming, which explains the emptiness without needing new physics. Fourth, we need to look at the energy budget using the Sunyaev-Zeldovich effect to find any missing hot gas. This method doesn't care about how far away something is. It only cares about the pressure of the gas. If massive halos are avoiding the void, then the thermal footprint of the interior should drop significantly. This is an energy census that can't hide behind dust or distance, and it gives us a clear look at what is happening. By stacking maps from the Planck satellite and measuring the radial profile, we can catch even the most subtle hints of hot gas. If the interior is quiet and we only see modest bumps at the rim, it strengthens the idea that no exotic explosions happen. But if we find a ring of pressure or an unexpected signal in the center, it means we missed a massive amount of heat, and that would crack the simple void story wide open. Fifth, we need to map the peculiar velocities to trace how gravity is pulling things around the emptiness. Gravity sets the currents in the universe, and the velocities of galaxies are like the die that shows us where the water is flowing. Dynamics don't bluff, and they tell us exactly where the mass is located. We can assemble distances using standard markers like supernovae, and then reconstruct the three-dimensional flow of everything around Boötes. We want to see the actual vectors of movement, not just a simple number. If the streamlines skirt around the cavity and funnel toward the rim at the right speeds, it closes the loop between mass, light, and motion. But if the flows are too strong or too weak, then either our gravity models are off or the surveys are totally overstating how empty the place really is. Here is how these 5 experiments actually fit together into one big picture. The radio sweep tells us if the engines are missing across the board or just the loud ones, while the gravity maps tell us how much mass actually left the area. The dwarf galaxy spectroscopy tells us if the halos simply failed to light up, and the energy stacks check to see if the hot gas skipped town along with them. Finally, the velocity maps tie everything back to the fundamental push and pull of gravity. Each of these tests points at a different part of the same problem, and if they all agree, we will finally know the true shape of the void. So what does this actually confirm or kill? If we see a clean radio dip, a soft gravity bowl, a flat interior population, and flows that match the mass, then the working model is confirmed. It means Boötes is just an extreme natural void with a strong bias against forming faint galaxies. But if we find a sharp edge in the background radiation and a compensated ring of mass, the model dies and we have to start talking about scars from the early universe. If the gravity maps show hidden mass and the gas looks totally normal, then the light was lying to us the whole time and gravity never actually budged. Any mismatch between these results will push us to question gravity itself. Either way, the situation is about to tip because these experiments aren't just ideas. They are already scheduled or currently running. When the data finally lands, this hole will either become the most useful, boring void we have ever measured, or it will be the first real hint that our map of the universe is missing a major rule. If a hole can rewrite the map, here's the thing that sticks with you after all the tests are done. One quiet patch of sky can completely tilt how we think about the truth in our maps. Boötes isn't loud or flashy, but it's incredibly stubborn. It keeps reminding us that it's real, it's massive, and it makes our scientific shortcuts show. Think of it as a cosmic humility check. We've spent years building this clean, perfect picture of the cosmic web, and then a giant hole walks in to remind us that even parts are just averages, not guarantees. Anomalies like this actually force us to do better science because they cut out all the wiggle room. You can try to explain away almost anything with hand-wavy talk about bias until you finally hit a case that demands hard numbers. Boötes did exactly that for our understanding of how galaxies form. It turned bias from a lazy fudge word into actual parameters you have to measure, like cooling floors in thin gas or the specific timing of reionization. None of that is just decoration. It's the entire point of figuring out how light turns into mass. When you finally get the physics of a void right, your precision work stops drifting and starts making sense. Now, why do these erased reality stories hook us so fast? It's because empty space with a clean edge feels personal, almost like it was put there on purpose. Our brains are wired to love borders and clear causes, But hold on, because what the sky actually gave us is a lesson in restraint. We didn't get crisp steps in the CMB or perfect rings or some hidden mass jackpot. Instead, we found faint nods that all line up, like fewer engines, lighter gravity, and flows that bend around a bowl. The real power of the story isn't that it's spooky, but that it stays coherent across different measurements that don't even speak the same language. Let's talk about the feeling of discovery for a second. Imagine staring at a massive survey you helped build and suddenly noticing a giant byte is missing from the data. Your first thought is the instrument, then you blame the pipeline, and eventually you start worrying about your career. Then months go by, and after every null test and blind injection and rotated mask you can think of, that byte is still there. I'm telling you, a moment like that changes how you walk into a team meeting. You start speaking a lot softer about your assumptions, and you find yourself asking for another control field before you ever celebrate a pretty plot. You actually get addicted to the boring answers that manage to survive. Meanwhile, something else is happening in the background that's just as important: the method. Work that puts the anomaly first doesn't just worship the weird thing. It uses that weirdness to nail down what's normal. That radio dip forced us to run much deeper tests on our data, and the lensing bowl helped us sharpen how we handle systematic errors. Even if Boötes ends up being just a big void, it has already upgraded the tools we use everywhere else in the universe. So what kind of universe makes a place like this normal? It's a universe where homogeneity is a promise kept statistically, but never locally. It's a place where you can drive for 300 million light years and almost never see a single city, only to hit a crowded rim and think you've found the only lights left. This universe hides its hardest lessons in low-signal terrain, like faint dwarf galaxies and thin gas. That means the next big breakthrough won't come from one spectacular discovery, but from thousands of careful, overlapping small ones that finally agree with each other. Get this, the broader meaning here is that our maps are lying to us. It's that maps tend to exaggerate when we ask them the wrong questions. We asked galaxy light to represent gravity, and it tried its best, but Boötes said not here, and not without context. So we learn from it. We let gravity speak in the places where light starts to stutter, and we teach our models how to breathe in these cosmic deserts. We have to stop rounding off the weird parts of the data, because the weird parts are exactly where theory earns its paycheck. And yeah, we're finally closing our loops. That erased sky radio silence looks more like a lack of engines than muted ones, with the faint end of the spectrum being more suppressed than we ever guessed. When we look at the natural or erased fork in the road, the sky keeps siding with natural causes plus a bit of bias, though there's just enough of an itch left to keep us honest. The stakes are still the same and maybe even sharper now, because if your maps skip the empty parts, they're going to fool you about the full ones. That's the real rewrite. One giant hole forcing us to write a much better script. That hole changes the whole bargain, proving that truth beats a tidy map when the empty places refuse to smooth out. If you want to see the follow-up when the new lensing and radio sweeps hit this patch of sky, make sure to subscribe and ring the bell. Share this with that one friend who swears space is uniform, because it definitely isn't, and that really matters. Watch the next episode to see how a local underdensity like this can actually tilt the numbers for the entire Hubble constant.